Okay, so for the audience that missed, it's just a beautiful first sunrise picture at the North Pole where I had my Raman instrument with me. So yeah, my name is Adela and I'm working with Katarina Abrahamson, professor in marine chemistry at Gothenburg University. And again, part-time I work at MMT as well. Let's see, might be a bit of a lag, like Anna said. It's quite a long lag. Okay. Nothing happens.
And it's not changing on your computer either.
Yeah. Why is that?
Can you maybe stop and restart the share?
Should I do a new share?
Yeah, just stop it and restart the share. Okay, so now it actually appears here.
Yeah. Let's go again. Okay, now feels like something happens. Yeah. Now, okay. So feels like we are back in business. Yeah, so what I'm gonna talk about, just a few things, the Raman, a bit of background, what is Raman technique, the spectrometer, our choices, difficulties we had and thoughts about it, and the test and results, what we managed to do until now. So yeah, what is Raman spectroscopy? The idea is that we have an incident light. So we are using a monochromatic light and we went for the 633 nanometer, which is red light. And you have the incident light that you put through the sample, like I showed you yesterday. And then usually you have a Rayleigh scattering and the fluorescence that are big signals. And then the Stokes, the Raman scattering and the anti-Stokes, we are not looking at that. We go just to Stokes scattering. They are very, very tiny signals. And it doesn't, the probability of that signal is very, very low as well. And we try to intensify that signal. So yeah, it's an inelastic scattering. And you see, like, you send one photon that has a specific energy and you get, the molecule starts to react, it starts dancing because of that energy, and it's excited and it sends you another photon back, and that we register as a Raman scattering. And of course, the wavelength is shifted. So you send like a lower wavelength and you get a higher wavelength. So if we send 633, we are going to look into the 100 nanometer difference. So from 640 to 744. So that's our detector going to register, because there is the signature of our chemicals compounds that we want to analyze. And the third pictures there, you see actually what's happening with the molecules. So they start vibrating and you have a stretch, you have a bending. So for me, it's like a dance of these molecules when they get the energy from the laser. Now this is one of my results, but what we see actually. So if we plot intensity to frequency, and then you see in that little equation how we calculate this Raman shift, which is the unit. It's called Raman shift or wave number. Then you see, like, you send the light, the excitation light, and then what you get back, and then you transform it in centimeters. So you get the unit per centimeter frequency. And then every molecule has a specific fingerprint, and we call them bands. And all those peaks you see there, they are from I'm using in this study pyrene. So it's a molecule that has 4 benzene rings, and it starts dancing when it gets the laser light, and it gives me those peaks of specific wave numbers. And I know exactly those are the pyrene signature. And they're always there. Doesn't matter what kind of laser wavelength you use, I'm always gonna get these numbers. Sorry, I need a bit of water. So the beauty of this technique is that we can have different lasers. So even if you can't identify a molecule with one specific laser, if you can integrate multiple lasers in an instrument, then you can switch between lasers. But then it comes with a bit of a problem because the spectrometer is built to register in a specific wavelength. And then if you change the laser, you kind of have to change the grating in the spectrometer as well. But there are different solutions for that. You can rotate the grating so you can register the numbers that you are interested in. And while we look at these specific numbers, it's because we call them as well like the biological window. So the molecules that we are interested in, they give us a signature in this window from 200 to about 2200 wave numbers. And that's why I was talking about the modes, and those are the peaks that you've seen in the previous slide. And on the first column is like from our experiments, like the one identified, and of course you have to compare with the database just to make sure that, you know, this we can use for our calibration as well of the spectrometer. So, and you see like what means actually when you get a mode, like what's happening in the molecule itself, and we call them vibrational modes. And you see those symbols there, and then translating more in English, you see when the molecule starts vibrating, when it's which bonds are vibrating or stretching, if it's the ring itself that starts dancing, or where exactly the excitation happens in the molecule. And why we try to do this? Of course, a really important thing, because the molecules gives you a fingerprint, we try to identify them, and the beauty is that you can identify them in soil samples, in seawater, or any kind of water, in air, so in different medium. And yeah, we are trying to look at, the focus right now is the PAHs, polyaromatic hydrocarbons, which are made from different numbers of benzene rings. So it's like carbon and hydrogen molecules. That's why polyaromatic, because the aromatics contain the benzene rings. And you see in the middle picture how they look like. And those are the 16 dangerous ones that are recorded by different environmental agencies. And we try to keep an eye on them, what's happening to them in the water. They don't like to dissolve in the water, so just in tiny, tiny amounts, 0.1 milligram per liter, they start to be soluble in water, and they accumulate in sediments. So we have really good data from sediments with these PAHs, but we want to detect them in water because they're in so tiny amounts. And yeah, I'm working with pyrene again, which is like 4 benzene rings, is the number 8, the second row, last one to the right. And of course, there are components of oil. And if we want to detect an oil spill, of course, we are going to look for PAHs. Another idea is like we can detect explosives, like nitroaromatics, TNT, for example. We can try to detect that. It's funny to watch explosions, but in a controlled medium. So those are our goals. Yeah, trace gas pipeline leakages, if we can detect that on different platforms, AUVs and ROVs, identification of UXO, unexploded ordnance, and the focus will be TNT. And of course, if we can find, you know, micro changes in the marine chemistry in the water, we can track the signatures of different submarines. So yeah, how we started, like you see in the picture, that's our millennial instrument. So it takes almost half of a room in the lab. It's a massive one, it's from the 90s. You have different lasers, you have a tower with mirrors. It takes 20 minutes to start the computer and then another hour to reboot it. And it takes like, I don't know, 30 minutes to 1 hour to analyze one sample. So of course we want to go down in size and we want to take a sample really, really fast. And the Gen Z instrument is a lot smaller, like you can see. And this is the one that I was presenting you outside. And then we can minimize that size even more. Because what you've seen outside, and I'm going to the next one. So the picture to the right is what you've seen outside. They're modular systems. So you have the laser, the big one, and then the spectrometer sits on top of the laser. And then you have a probe, which is coupled with fiber optic cables. And inside you have like a cuvette holder or a sample holder where the laser light goes through. And the signal goes through back to the fiber cable into the spectrometer and gets analyzed. So that little thingy, 30 by 30 by 30 centimeters, can be theoretically minimized to 30 by 30 millimeters. So we can really go down in size with the spectrometer itself. The laser as well can go a lot down in size, and then everything can be incorporated in one unit. Yeah, so how we minimize this size. So just looking at the spectrometer itself, there are some components that are very, very important in minimizing the size. And one important component is the diffraction grating. And of course, the more lines, it's actually a unit that it has a number of lines per millimeter. So it's called grooves. And if we increase that one, like you see in the equation, like the focus length gets minimized. And of course, we look as well at the length of the detector. So now the detectors, the CCD detector that we have on the market, they can be between 1/4 of an inch to 1 inch. And of course, you need to think about resolution. So it's a trade-off as well, like how much light throughput you want through the spectrometers to the size. And that's why we look at grating detector, which is important for our resolution, the slit size as well, that gives you the beam, the image of the beam that ends up on the detector. So these are like very particular, and of course it comes down, okay, how many pixels you have on the detector, yeah, the F number, the aperture number of the spectrometer itself. So we are working with Wasatch Photonics to minimize this part. So this is doable. It's nothing that is not on the market or we need to develop. It's a matter of what we want to get out of the spectrometer. And of course, we want resolution and we want a signal in very, very fast time. And from that, we can design our spectrometer. And this is what we managed to get after looking at different companies, what they offer and what we want to get from a spectrometer and the Raman system. And these are like the technical aspects. And of course, we want, the resolution is quite good. 5 per centimeter, you can go down to maybe 4.5 to 3 from the small, tiny systems. Like if we have a massive one, a benchtop in the labs, you can go to 0.1. But that's difficult to take it on a platform, underwater platform. So, but then the resolution, can be fixed a bit with the slit size. So on that we can work on. And of course, the detector we can work on. We can go even smaller detector to minimize size, but we don't want to use that resolution. The most important thing for us, it was integration time. So we want to use a very fast pace in obtaining the spectrum. And this instrument can give you a spectrum in 22 milliseconds, which is really, really good. And of course, you can do averages. You can take 10 averages or how many you want in order to get a beautiful curve at the end. But if you have a long integration time, that time will increase if you add the averages on top. And of course, very important for us, the signal to noise ratio. And we opted for a cooled detector that improved the signal to noise ratio 3 times. But that means a bigger size because you need to cool the detector. So, but you've seen the instrument outside, even if it's small, it has a cooled detector. Yeah, and the power consumption, that's really nice. And our laser is like 50 milliwatt. We don't want a higher laser because that might destroy, you get photo bleaching, it might destroy samples that you want to analyze. So we want to keep it there like 20 milliwatt, maximum 100 milliwatt. It's good for us for what we want to analyze. Okay, I'm talking quite a lot. Results, so yeah, we try to get first the best of the spectrometer without enhancing any signal. And you see some concentrations there. it goes, I mean, we try different concentration, but you see that we don't see what we want to see. We want to go down to microgram to even nanogram per liter. So what you see there, we are in the milligram per liter. And the spectrometer itself is doing very good if you want to analyze high concentrations. But if we want to go down in concentrations, then we have to think differently. Again, it's just zoomed in on the peaks and it's basic processing on the data, and you see those peaks, what are created by what's happening in the molecule giving you the signal. And then we introduced the idea of surface enhanced Raman spectroscopy. And the idea is like to use metals in nanoparticle size, because the optical properties of the metals are changing, and we focus on gold and silver. And the idea is like to enhance the signal from the analyte due to this enhancement in the nanoparticles. So what's happening, you have a chemical enhancement and you have an electromagnetic enhancement. So the chemical enhancement, usually it's double folded, and the electromagnetic enhancement, if you do it right, you can go to 12 folded enhancement, which is really, really good. So you want to reach the maximum enhancement from these nanoparticles. But it's very tricky because it's a bit of witchcraft, how I'm saying. You need to prepare them, so you boil them. It's chemistry. It's always you boil things in chemistry. And then, of course, it will help if you have access to an electron microscope, so you see the size, the shape of the nanoparticles. But with Corona, everything being closed, all the labs being closed, it was like looking at the color and guessing a bit more like, okay, is it good? Testing. Let's see how the results will look like. So yeah, I'm working with colloidal solutions, so liquid form with nanoparticles, because it's easy for testing. If I run hundreds of tests, I do not have time to dry them, put them on a substrate, analyze. That will increase my testing time a lot. But once we have a result in the liquid form, it will be just to transform them in a dry form. So we are going to put them on a surface, and there are different methods to do that. Yeah, I have some pictures of the silver nanoparticles, and we see they are quite big, different sizes, they are round in shape. And the idea to get the higher and higher enhancement, you need a kind of a matrix of these nanoparticles. So if you have junctions, and if they are like really rough, and people are trying to design them, so they are pyramids, they are stars, they are cylindrical forms, you can create them in a chemical form, you can do lithographic printing. So it's a lot going on when it comes to nanoparticles. But the idea is we want to get them close enough to create these junctions to enhance my signal, because the molecules are getting stuck in these junctions. And if you have like V-shaped junctions and troughs, even better than the round shape. But you don't want them too tight together either, because that can lower your signal. So you don't want too much aggregation. And that was another idea we worked with to overcome the kinetics and the chemistry, to create this aggregation that will enhance my signal and the reaction time. So yeah, it's how they look. The reddish color, gold, and dark green, yellow color, silver. Yes, so I was talking about the size is very important, and the roughness and aggregation is very important for us. And this is the results that that we managed to get with silver. Silver is very tricky to prepare them and to get the right size to give you the right enhancement for the molecules we analyze. And here is just a reference. We try to go down to 10 milligrams, a bit hard with silver to actually detect 10 micrograms per liter. And then, of course, we tried with gold, because the metals have different properties and molecules prefer different metals. And it will be nice to combine these two metals in a substrate to get more out of the enhancement. And then we tried, these are really good results with gold nanoparticles. And you see, those peaks that are given by the pyrene molecule, really nice peak at 500 of course, to make them beautiful and do a lot of averaging. But what we can do, and this is Katarina working with, we can apply different models. This is a statistical model that she's working with. It's like, can we actually see PREN? Like, is it wishful thinking? Like, yeah, I see it's a peak, you know, low concentration, but is it just me seeing that and I'm happy with that? And then we have to apply different models. And these are for the low concentration. You have all the concentrations from, yeah, the lowest one is 10 microgram per liter. Those numbers are actually millimolar, but the lowest number is 10 micrograms per liter. And you see for the lowest concentration, so Katarina knows more about this. I've just seen it in action. I don't have knowledge about these statistical models, but the idea is like, what are the components in the data that she's looking at? And then she's comparing to a reference, and the reference is our pyrene, the typical signature of pyrene, and you see it in blue. And then you compare the components, and this is the leftovers in the small concentration, and you see that we get the peaks, or we should have the peaks in pyrene. So statistically, we can see that we have parts, 10 micrograms per liters. Even with the visible eyes in the spectrum, you don't see it. By applying these models, you actually see it is there. And then you compare the second graph to the right, you compare to the reference. Is it actually there? So the more they are alike, the more you see it there. So we are happy with these results that we can statistically see actually that we have in low concentrations, and we're going to go even lower to see if we go to nanograms per liter. And yeah, these are the futures plans, like tuning the substrate, the nanoparticle substrate, and we look like different technologies that are out there, and that will not take time. Of course, we want to create them ourselves, but we'll see if it maybe works better with lithography. That's like 3D printing of nanoparticles on a substrate. It's super cool technologies. And then, of course, we want to continue with the multivariate analysis, and John will help us with machine learning. And hopefully we see even more in the noise than we actually see. And of course, a big thing will be now design and reintegration and rebuild the sensor. I was talking a lot, sorry. But I'm done.